Today, we're going to continue our discussion of dimension reduction, but we're going to look at dimension reduction of sparse vectors. We say that a vector x is k-sparse if x has only k non-zero coefficients. We're going to use this L0 norm notation to denote the sparsity of x. Note that this is a bit of an abusive notation. This is not actually a norm. Sparsity shows up all over the place in real-world data. For example, some images, like this one of the night sky, are naturally sparse, or at least they are approximately sparse, meaning that most of the coefficients are either 0 or close to 0. Other natural images, like this one, aren't immediately sparse to look at, but they do turn out to be sparse, or approximately sparse, when you write them in the right basis. For example, this here is the discrete wavelet transform of this castle image, and you can see that most of the pixels are 0. Similarly, a lot of naturally occurring audio signals, like human speech or music, also become sparse when you write it in the right basis, for example, when you take a Fourier transform. Given that sparsity is everywhere, today we're going to look at the problem of embedding sparse vectors. For some motivation for this, let's recall the Johnson-Lindenstrauss lemma that we saw previously. The Johnson-Lindenstrauss lemma says that any n-point set in R to the d can be embedded in R to the m, where m is big O of log n over delta squared, with distortion 1 plus delta. That is, we can embed any n-point set in a much lower dimensional space with not too much distortion. Today, we'll encounter a similar phenomenon for embedding sparse vectors in a lower dimensional space. Instead of starting with an n-point set, we're going to start with the set of all k-sparse vectors in some n-dimensional space. For example, in this picture here, I've drawn a cartoon of all the 2 sparse vectors in R3. Note that this is an infinite set. We're going to try to embed this infinite set into Rm, where m is big O of k log n divided by delta squared. And we want to do it in a way that approximately preserves distances, up to distortion 1 plus delta. More precisely, we'll look at something called the Restricted Isometry Property, or RIP. We say that a matrix A in R to the m by n has the restricted isometry property with parameters k and delta if for any x in R to the n, with sparsity at most k, the L2 norm of A times x is equal to the L2 norm of x times 1 plus or minus delta. Notice that if A has the restricted isometry property with parameter k, then it preserves distances between all k over 2 sparse vectors. In other words, it's a 1 plus delta embedding of these k over 2 sparse vectors into R to the m. This property is called the restricted isometry property because restricted to each k-dimensional coordinate subspace, the map A times x is approximately an isometry. That is, suppose that this is my matrix A. So A is short and fat. If I multiply A by some k-sparse vector x, let's say that this is the support of x, it has size k, then I'm restricting my attention to the corresponding k columns of A. And the restricted isometry property says that this matrix, this m by k matrix, is an approximate isometry of R to the k into R to the m. Okay, why do we care about this definition? One application is something called compressed sensing. The mathematical setup for compressed sensing is the following. Suppose we have some short fat matrix A, it's m by n, and we want to multiply it by some long sparse vector x. So x lives in R to the n, where n is big, but it has only k non-zero elements, where I think of k as being much, much less than n. We see this outcome, A times x, and the goal is to recover x. Now, if we didn't have the sparsity assumption, this would be impossible. This here is an underdetermined linear system, and so there's a whole subspace of possible solutions x. However, It turns out that sometimes, if A is nice, exactly one of those solutions is going to be sparse. So it turns out that if we impose this extra sparsity assumption, we can recover X exactly, even given this tiny amount of data. This problem comes up in a variety of applications. For one motivating example, suppose I'm sampling some signal, like an audio signal, that's sparse in the Fourier domain. That is, I have some audio signal that's just sort of going on and on and on, and I just want to occasionally sample it in time. It turns out that my observations are going to end up looking like this: A times some sparse vector, where in this case A is going to consist of rows of the discrete Fourier transform. The question we want to answer in this signal processing application is, can I recover the original signal given just these few samples? And in particular, how few samples can I get away with in order to recover X, or recover X approximately? This corresponds to wanting A to be as short as possible, to have as few rows as we can get away with. In this context, the reason we care about the restricted isometry property is that if a matrix A has the restricted isometry property, then we can recover that sparse vector X in the problem on the previous slide. To see why this should be possible in principle, suppose that A has the restricted isometry property with parameters 2k and delta equals, say, 0.1. Now I claim that there is a unique k-sparse vector X that agrees with our observations A times X. Indeed, if X and X prime are both k-sparse, and they have the same observations, that is, AX is equal to AX prime, then if A has the restricted isometry property, the L2 norm of X minus X prime is at most 1 over 1 minus delta times the L2 norm of A times X minus X prime. But AX is equal to AX prime, so this is just 0. So in particular, this implies that X equals X prime, and so there's a unique solution to this system. This gives us an inefficient algorithm to recover X. We'll just find the sparsest vector, X hat, that agrees with our observations. So X hat is going to be the argmin over all Y of the sparsity of Y, such that AX is equal to AY. Unfortunately, as we just noted, this does not give us an efficient algorithm. It turns out to be computationally difficult to find the sparsest vector that lives in some affine subspace. So this leads us to the real reason that we want the restricted isometry property in this application. The restricted isometry property was overkill for the previous slide. There are weaker conditions that guarantee inefficient recovery of X. But the reason we want the RIP here is that if A has the RIP, it turns out that we can also recover X efficiently. We're not going to go into the details in this video, but here's the basic idea. On the previous slide, we said that we wanted to solve this problem, find the sparsest Y that agrees with our observations. And we said that that was hard. But what if instead we consider this problem? Let's find the Y with the smallest L1 norm that agrees with our observations. You can view this as sort of a relaxation of our original problem. This second problem is nice because it turns out that it's efficient to solve. You can do it by solving a linear program. Moreover, it turns out that if A has the 2k RIP, then these two problems are the same. That is, the X hat returned by this first problem is the same as the X hat returned by this second problem. I'm not going to prove this theorem now, but here's the basic intuition. Suppose that the setup looks like this. Here's R to the n, and here's the affine subspace consisting of all the vectors y, so that A times y agrees with our observations. It's equal to A times x. Now we ask ourselves, where does this X hat live? Well, it should be the element of this subspace with the smallest L1 norm. To understand the geometric intuition for that, let's consider what the L1 ball looks like. So here's the L1 ball. This is the set of all vectors y with L1 norm at most 1. In order to find the vector in this affine subspace with smallest L1 norm, we basically just imagine puffing up this ball until we hit that space. And the point where the ball hits, right here, is going to be the minimizer. So this is x hat. And you note that in this example, x hat just happens to be sparse. In this case, in this sort of two-dimensional picture, it happens to be one sparse. It lives on the x-axis. But you can imagine this kind of happening more generally in higher dimensions. The L1 ball is kind of pointy. It has these points that kind of stick out. And those points are likely to be the thing that hit this affine subspace first as you start growing this ball. And that's intuitively why this theorem is true. You can check out the lecture notes for some references if you want to see the actual proof, although it's not really necessary for what we'll do going forward. Okay, so now that we've somewhat motivated the restricted isometry property, we might ask what matrices have the restricted isometry property, with some parameter k and let's say delta equals 0.1. And in particular, how few rows can we get away with? For our applications, we're going to want the target dimension m to be small. There's a lot that's known here, but here's some of what's known. First, suppose that A is a random matrix with independent Gaussian entries. That is, every entry is some independent Gaussian with mean 0 and variance 1 over m. Then it turns out that if you take m to be big O of k log n, this matrix will, with high probability, satisfy the k-restricted isometry property. Second, motivated by some of the examples we mentioned earlier, as well as other examples, suppose that A consists of random rows of a discrete Fourier transform. That is, every row here is some row from the DFT, and we just choose all the rows independently. Again, it's known that if m is a little bit bigger, big O of k polylog n, then this matrix is going to have the restricted isometry property with high probability. As a side note, understanding exactly the number of rows you need for this to hold with high probability is one of my very favorite open questions. Great, so that gives us two random ensembles of matrices which, with high probability, have this nice restricted isometry property. But we might ask, do we really need the with high probability here? The definition of the RIP doesn't have any randomness in it. Maybe I'm only introducing randomness because it's randomized algorithms class and I feel like I oughta. Well, in fact, while we don't technically need the randomness, we don't actually know any deterministic constructions that are nearly this good. That is, the best deterministic constructions we know have parameters something like this. That is, they need about k squared rows instead of about k, or technically k to the 1.99999. So this is a factor of k off of the optimum, which can be significant. So this is a case where randomness really helps us out, even though it might be that we could one day come up with some deterministic construction. Okay, so that's it for this video. In the next video, we're going to prove this result, that a random Gaussian matrix has the restricted isometry property with high probability. See you there!